In the section 6.4, we're going to continue to take derivatives using all of the derivative rules that we've seen already. But we're going to need to pay close attention to whether we're dealing with an x variable or a y variable. So everything that we've seen so far, our equations have been y given explicitly in terms of x. So that's what I have on the left here. And basically that means that the variables are separated. So you've got the y variable by itself on the left, and the x variable, maybe with other stuff, but on the right. And what we're going to look at in this section, though, is what if those variables are mixed together and we can't actually isolate the y. So we can use the same derivative rules, but there's going to be one extra step that we need to add to that. Okay, here's kind of a breakdown what's happening with implicit differentiation, and then I'll kind of summarize it. So first is, if we focus on some of the notation, this means take the derivative with respect to x. We haven't really talked about this notation much because we've been working primarily with the variable x, and when the variables match, there's not anything extra that we need to do. And so if we look at on the left here, we're taking the derivative with respect to x, but the variables match. So from what we know, the rule is to take the derivative of x. The answer is 1. What's going on behind the scenes, though, is that when you take the derivative with respect to x and the variable is x, they match up. And that actually ends up looking like dx over dx, which simplifies to 1 just like any fraction we had. If we have the same thing in the numerator and the same thing in the denominator, that would also simplify to 1. If we look at some other examples, so if we take the derivative of x squared, using the power rule, that gives us 2x, but we should multiply by that same fraction from before. So we're taking the derivative of x, that's the x in the numerator here, with respect to x. And so they match up. So basically that goes away, leaving us with just 2x, which is, what we've seen, right? We've seen take the derivative of x squared, the answer is 2x, and we're not talking about any of that dx over dx that's going on behind the scenes. Same thing for x cubed. So if we use the power rule here, that's 3x squared. But if we consider this idea that we're taking the derivative of x with respect to x, you actually multiply in this fraction, but the fraction ends up being 1. So our answer to that is just 3x squared. The thing is with y, we can't skip that part because it's not going to simplify to 1. So if we do the same thing, so you notice this in the beginning is saying we're taking the derivative of our expression with respect to x, but now we're dealing with a different variable. So for that first one, if we want to find the derivative with respect to x of y, if we sort of write that as our fraction, it becomes dy over dx. This does not simplify, so the answer is dy over dx. So basically, whenever we take the derivative of a y, there is going to be a dy dx that's part of our answer. So if we look at the next one, d over dx, so the derivative with respect to x of y squared, we can actually start by applying the same power rule. So its quantity is squared, so we bring the 2 down, the exponent becomes a 1, so that just leaves 2y. But we have to multiply by this fraction, taking the derivative of y, so dy over dx. You could actually look at this as an extension of the chain rule, which is that once you take the power rule, the last step is to multiply by the derivative of, in this case, y, and the derivative of y is dy dx. If we look at y cubed, we can apply the power rule, so that's 3y squared. But again, if we think about this as the chain rule, the last step is to multiply. Well, what is the derivative of y? Well, that's because the variables didn't match, it ended up being dy over dx, and that's going to be part of the answer. And so the summary that I was talking about, is that whenever you take the derivative of y, regardless of what derivative rule you might use, you're going to have to multiply by dy over dx. So let's look how this is going to actually look in the examples. Okay, so this first one is actually an equation that has y written explicitly in terms of x. So that means that we're not really doing anything different from what we had been doing before. I just kind of want to show it to you with this new notation. And so if we would take the derivative of this, I'm just going to look at the right side first. Everything on the right side has x's, no y's, and we're taking the derivative with respect to x, so that means everything's the same. So to take the derivative here, it's going to be 7 times the derivative of x squared, which is 2x, plus 9x, the derivative is 9, 10, the derivative is 0. And I can simplify that to be 14x plus 9. But now I actually want to talk about what's going on the left side. We were actually taking the derivative of y with respect to x, so the y actually turns into dy dx. And you might have seen that notation before, but we've only had it on like the left side of the equation, where now in our later examples we're going to actually start integrating it into the x's as well. So this is just really what we've done before, but just now using that new notation that I was talking about. Okay, so here's an example though, where as you see on the left, the x's and y's are together on the same side of the equation, and you do not have y isolated. So this would be an example where you have y written implicitly in terms of x, which means now we need to use implicit differentiation. And when it says dy dx, the first thing that we're trying to do is take this whole equation, and we'll do both sides. We want to take the derivative with respect to x. And so you could write that in parts if you wanted to. So we need the derivative with respect to x of 6x squared. We're also going to need to take the derivative with respect to x of y squared equals, and we want to take the derivative with respect to x of 36. So you don't have to write it out this way, but basically we're just, you take the derivative of each part. And we can take those derivatives separately. So for the first one, we're dealing with the variable x, which matches here, so nothing new. We're just going to take the derivative of 6x squared. So that's going to be 6 times 2x, or 12x. I'm going to skip over the y for a second and just do the right side. So the derivative of 36, well, there's no variables here and nothing changes. Whenever you take the derivative of a constant, the answer is 0, so this is going to be 0. But now let's go ahead and look. This is the new part here. So we're going to take the derivative of y squared, but with respect to x. So now that those variables are not matching is when we're going to need to do that extra step. So first let's go ahead though and take the derivative of y squared just using the power rule. So that's going to be 2y. But whether you look at it as a chain rule or just whenever the variables don't match, you have to multiply by dy over dx. And so I have the problem kind of spaced out a lot, but let me just go ahead and rewrite it. We've got 12x plus 2y dy dx is equal to 0. So here we've taken a derivative using that new concept of dy dx. The thing is that we're not actually done at this point. So we've taken the derivative, so we're done taking the derivative. But when we have these problems where we're actually trying to find dy dx, what we're trying to do is take the derivative first, but then get that y part, dy dx, by itself. So then we have to do a little bit more work to just isolate dy dx. And we're not going to use any derivatives to do that. We're just going to use algebra. So like in this case, I could subtract 12x from both sides. So that would leave 2y times dy dx is equal to negative 12x. And then now, to get dy dx by itself, I could divide both sides by 2y, so that leaves dy dx is equal to negative 12x over 2y, which this simplifies, so I could rewrite it as negative 6x over y. So this is our derivative now, but really because our original equation had the x's and y's sort of mixed together, we would actually expect that the derivative would have the same thing. So our derivative here has the x's and y's mixed together. Remember, the derivative we could use to find the slope or the change of something, and that doesn't change here. It's just that if we wanted to find the slope, we're going to have to plug in the x and y in order to come up with that slope, and we will do an example like that later. Let's try another one. Okay, so here we're going to find dy dx. So the first thing is we're going to take our equation and we want to find the derivative with respect to x. So that's the left side and the right side. This would be a case where, I was saying before, we dealt with equations where the x's were on one side and the y's were on the other. That's technically happening here, but we don't have it isolated as just a single y is equal to something. That's how it was written for all the problems that we've seen previous to this section. So let's take the derivative here. So I'm going to write it in steps again. So we want the derivative of 3x squared, and we're also going to find the derivative of 2 minus y over 2 plus y. So the left side is going to be nothing new. So the derivative of 3x squared is 3 times 2x. I'm just going to write it and simplify it as 6x. But we do need to do a little more work over here on the right. So we've got y's in there, so I know I'm going to have to, at some point, multiply by a dy dx. I'm also going to go ahead and use the quotient rule for this one. And one thing to note about multiplying by dy dx is you don't just multiply the whole thing by dy dx. You multiply any time you actually take the derivative of y. So this is really important with the quotient rules because sometimes you're not taking a derivative, you're just putting an expression there. And at that point, you wouldn't have to do that multiplication. Okay, so I think it'll make more sense when I actually start to write it down. So the quotient rule, okay, I'm going to need a big fraction, so let me start with that. The denominator is the denominator squared. So this is going to be 2 plus y squared. I'm not multiplying by dy dx because I have not taken any derivatives. The quotient rule just says rewrite the denominator exactly as it was, but just square it. So that's what I've done. So the numerator part of the quotient rule is where we will start to take the derivative. We will start to take derivatives. So first thing I do is it's the denominator again. So not taking any derivatives, but just writing the denominator. So all I'm doing is just writing the denominator again, which is 2 plus y. I have not taken the derivative of it, so I don't need to multiply in a dy dx. But now we're going to take the derivative of the numerator. So to just remind us that's what we're doing, I'm going to write the derivative of 2 minus y. So what's the derivative of 2 minus y? So first, just treat it like it was an x as a starting point. So if it were the derivative, I'll erase this in a second, but if it were the derivative of 2 minus x, the answer would just be negative 1, because the 2 goes to 0 and negative x becomes negative 1 when you take the derivative. So same thing here, which is that the derivative of 2 minus y is actually going to be negative 1. But since I'm taking the derivative of the variable y, I have to multiply in dy dx. And now let me keep going. I'm going to continue to use the quotient rule. Minus, now we can write the numerator. I'm not taking a derivative, so I don't need the dy dx. I'm just exactly writing what was in the numerator, not making any changes. Multiplied by the derivative of the denominator. So let me write that in here. So the derivative of 2 plus y. So since I'm taking the derivative, I do need to keep in mind this concept of dy dx. But before I do that, I just want to take the derivative of 2 plus y. So the derivative of 2 plus y is actually a positive 1, because the derivative of 2 is 0, and the derivative of y is 1, because the derivative of x is 1. But since our variable was y, we need to multiply in dy dx. So now I've actually done all the work for the derivative. It's simplifying at this point. And so let me just go ahead and try and rewrite this. So we've got 6x, and this is 2 plus y. I'm just going to, I guess, write that as negative dy dx minus 2 minus y times positive dy dx all over 2 plus y squared. Now let's work on simplifying this. So even though it's dy dx, we can still, there's a couple different things we could do here, but we just are following the rules of algebra, essentially, just as if it were an x or a y or something like that. So some things that we could do is we could distribute, or we could factor it out. So maybe in this case, since I can see that this term has a dy dx and this term has a dy dx, I'm sort of tempted to factor it out to maybe simplify some steps later on. So I think I'm going to go ahead and do that. So then if I rewrite it, I've got 6x is equal to, I'm factoring out a dy dx, and then what's left over in the numerator, we've got 2 plus y, and I've sort of left this negative 1 behind because I only took out the dy dx, minus 2 minus y, and then when I took the dy dx, you could have just left it blank because basically it's gone. I just sort of left a 1 as a placeholder all over the denominator. So it still looks a little messy here, so at this point I think I'm going to go ahead and just try and simplify this numerator here. So let me just kind of write that off to the side. So if we distribute the negative 1, we end up with negative 2 minus y. And then you got to be careful always with the quotient rule with negatives. So I'm going to put a negative, that whole thing in parentheses. So there's not really much to distribute there because that's just a 1, so it's going to be 2 minus y. But in order to get rid of these parentheses, I need to actually distribute the negative to both terms. So it ends up being negative 2 minus y minus 2 plus y. So if we keep going, you might notice here that the y's end up canceling, and I just get negative 4. So that whole part in gray actually simplifies to negative 4. So let me rewrite it. 6x is equal to dy dx times negative 4 all over 2 plus y squared. So what I'm doing at this point is I've simplified because of all the messiness that came from the quotient rule. But remember that when we're trying to find dy dx, the very last step, once you've taken the derivative, is to isolate the dy dx. So that's going to be the last part that I'm going to do for this problem. So to isolate it, I can multiply the 2 plus y squared on both sides. And if you want to do it at the same time, you could divide both sides by negative 4. And that actually leaves dy dx is equal to 6x times 2 plus y squared all over negative 4. And then I could simplify this a little bit because I have the 6 over 4. So I could write this as 3x times 2 plus y squared all over negative 2. And that would be the final answer. Just like regular derivatives, you can sort of look at it as the formula for the derivative or the formula to find the slope. Okay, now let's look at this example. So for this example, I want to go over this example because it kind of ties in some stuff that we've looked at earlier in the semester, which is taking the derivative and finding tangent lines. And I want to show you that you can do the same thing with implicit differentiation. So one thing that's different is that when you've got an equation written like this, where the y is not isolated, is that you can get some interesting curves. It's not a function because it doesn't pass the vertical line test, but it still is an equation that we could find the derivative and we can find slopes at any point on this graph. So in order to find the tangent line, one thing to remember is that to find the tangent line, we use the derivative to get the slope. So the first thing we need to do is to find the derivative. So let me rewrite the equation. And what we're going to do is we're going to take the derivative with respect to x. And so just kind of looking ahead, the x cubed is going to be a regular derivative. Y cubed, we'll use the power rule, but we also need to multiply by dy dx. This one, we're actually going to need to use the product rule to take the derivative of. And you could put the 9 on either part, but it's like, because there's two different variables here, you would want to treat it as two different functions, which you could call one u, one v, or however you've been labeling them when you use the product rule. Okay, let's do the left side first though, because that one is more straightforward. So the derivative of x cubed is 3x squared. The derivative of y cubed is 3y squared times dy dx. Equals, now let's use the product rule. So for the product rule, I don't know which one you've been starting with. Because it's addition with the product rule, it doesn't matter which one you do first. So let me just start with the 9x. So the 9x, I haven't done anything with it, so I just left it as a 9x. But now I could multiply by the derivative of y. The derivative of y, if you treated it just like an x, would be 1. But since the variables don't match up here, that's why we need to multiply by dy dx. And then plus, now we could leave the y alone, but we could take the derivative of the 9x, the other part of the other function that we're using for the product rule. So the derivative of that is 9. And the variable was x, so we don't need to multiply anything extra in there. So this is our derivative. Now we just need to simplify. So let me just try and rewrite it a little bit first. Okay, so here's the derivative. But now our last step is to get dy, to isolate dy dx. So you'll notice that we've got 2 of them this time. So with algebra, if that happens, what we want to do is we just want to move every term with a dy dx to one side and everything without a dy dx to the other side. So it doesn't matter which side we move things around to, but I could, for example, subtract 9x dy dx from both sides. And by doing that, it'll cancel out on the right side. So that's basically moving everything with the dy dx to the left. And at the same time, I could go ahead and move everything without, which in this case is the 3x squared. I could subtract it so that it moves everything without dy dx to the other side, or the right side. So that leaves us with 3y squared dy dx minus 9x dy dx is equal to 9y minus 3x squared. Okay, so what happens is if you get to this point, if you have everything with a dy dx on one side, like we have on the left, now that means you can factor it out. Because the trouble is here, it still looks like we have two of them, and we need to have just a single dy dx. So I'm going to factor the dy dx to the front, and then what we have left over in these parentheses is going to be 3y squared minus 9x is equal to, and I haven't changed anything on the right here. So now at this point, the last step to get dy dx by itself is going to be to divide everything by 3y squared minus 9x. And so at this point, we've found our derivative dy dx. And now if you recall, our goal was to actually find the tangent line. So let's go back and look at the question. We wanted to know the tangent line at the point 2, 4. So we could go ahead and find the slope. So one thing about finding the slope is that since our derivative has both x and y in it, this is where I was saying you have to actually plug in an x and a y. And if you have an ordered pair, well, that means that x is equal to 2 when y is equal to 4. So that's what you plug in to find your slope at that point. This will give us the slope at the point 2, 4. I'll just kind of write that in here. So the slope at 2, 4 is going to be 9 times 4 minus 3, x would be 2 squared, 3 times y, so that's 4 squared, minus 9 times x, which is 2. And then we can go ahead and multiply. When you multiply this out, you should get 24 in the numerator and 30 in the denominator. And then you can simplify this since both the numerator and the denominator are divisible by 6. So this would be 4 over 5. So that's the slope at the point 2, 4. And at this point, we're not going to do anything new. We're going to do what we have done before to find those tangent equations. So I'm going to write it as, if you know a point and a slope, you can find the equation by using this formula, the point-slope form. So that would be y minus, our y value is 4. Our slope we found to be 4 over 5. X minus, our x value is 2. And then just simplify this. Simplify this by getting a common denominator. If I can fit the final answer on here, we get that y is equal to 4 over 5x plus 12 over 5. And so this equation is actually the equation of this line, this tangent line.